accurate kinetic measurements, which could never be interpreted because there was no such thing as temperature. It's an interesting system. Anyhow, when I came to what?
There was a collision gas.
No, there were no collisions at all. There was no
maybe.
molecular decay. There was completely. It was a unimolecular reaction in which there were no collisions and there was no Boltzmann distribution. And the way the problem was eventually solved was some students of Heilbronn in Switzerland had created a machine called the photoelectron-photoion coincidence spectrometer. You put an electron, you put a photon in, electron comes out, and so you know the energy of the molecule that's been energized. And so you have what's called microcanonical space. So this was a time in my life when I was living alone, and my molecules were all alone also. But then I came to a point in my life that became highly cooperative. So I moved to polymers. And the question that arose with polymers was, you hear cooperativity all the time with polymers, just constantly, how cooperative they are. It makes sense that they should be a highly cooperative system. They're highly cooperative both intermacromolecular, in their relationships, the chains with each other, and they're also highly cooperative within each other. And so, being a student of Winslow and interested in stereochemistry, I was quite interested in connecting the two C's, cooperativity and chirality. And I learned about a polymer that had been made at DuPont. When DuPont lost their patent, this is going to go on for hours. But when DuPont lost their patent on the nylon 6,6, they'd already lost it on nylon 6 because Carruthers had published that it couldn't be made, and then the Germans figured out how to make it. But the nylon 6,6, when the patent was lost, it expired, they were desperate. They had lived so long on that, they wanted. So they created a polymer called the nylon 1. It was essentially just an isocyanate that is anironically polymerized. It doesn't matter what the structure is. It was a beautiful fiber. You could make gorgeous things out of it. You could dye it. It was absolutely perfect, except for one problem, that at the boiling point of water, it completely decomposed. So it was a complete loss. But there are Marshall Fixman and Stockmeyer and all of these physicists who were interested in polymers were fascinated by this polymer because it had what they discovered was, by light scattering, a very long persistence line. It's quite stiff. In other words, if you draw a tangent to the polymer at any point, and then you go down the chain, very far away down the chain, you'll find that the tangent to this place on the chain and that place on the chain are not very different from each other. So the chain is pretty much straight. So that means it has a big persistence, and anything that has a persistence like that in one direction has to really exist in a fairly deep energy well. Because if it didn't exist in a deep energy well and it could change its local shape all the time, it couldn't possibly be going on in straight. So the question is, what was the energy well? And that was discovered to be a helix. You couldn't really get a crystal of such you can't get a single crystal of a high polymer, but you can get fiber diagrams and you can see generally what's going on. And it was a helical combination. And so people were saying, well, what could be the source of the limit to this persistence and direction? The source of it could be just random local fluctuations that accumulate. But it also could be a helical reversal, because this helix, in contrast to biological systems, had no information to be left over. So you could imagine going along for a while, in this deep energy well that had to existed for the persistence. And then, but eventually, accumulating enough energy to reverse from left to right, that would certainly put some kind of kink in there, and change direction. So this could, and the physicists were trying to figure out what the source of those were the days when you could do things that were useless.
Get money for it, you mean, get paid.
Yes, Larry.
You can always do things useless. It's when someone pays you.
Yes. Now, so anyhow, I didn't care about that problem that much, but the idea of a helix that couldn't tell left from right seemed pretty interesting. And the other thing that seemed interesting is that it had to be very cooperative. Because, after all, if it existed in this deep well, and the helix was going along for a long time in the same way, left or right, if you put a little information in there saying be left or be right, and you put the information in on each unit of this chain, there are many units along this long length, it seemed reasonable that they would add up, the quantity. In fact, in the Japanese, in the ancient Chinese, cooperation and amplification are the same. I had that in the Non-Galanta review. A large number of small forces adds up to a large force, so that cooperativity would have to have an amplification associated with it. So and you had to put some chiral information in order to give it some information to be left and right. So what's the smallest of, if you're going to get an amplification, you want to use something small. So what's the smallest thing you can think about? Difference of a neutron, in other words, a stereogenic center, in Misley's way of speaking, which would only be stereogenic by virtue of hydrogen versus deuterium. And so this polymer had alkyl groups hanging off with CH2, several CH2 groups. So why not take one of those and take off the hydrogen and put deuterium on there, so you could get a chiral carbon by virtue of this chain. This could be done biologically by fermentation methods. And so we did that experiment. And what we expected was that small chiral effects will be amplified. So that having this helix care if it's left or right by virtue of a deuterium-hydrogen replacement has got to be a very tiny perturbation. So let's see if it can do anything. So we made this molecule. This is what we call the monomer. You can make the polymer from this. And it had a very tiny optical activity. In fact, there's an interesting literature you can read about. Ernest Illiel wrote in Topics in Stereochemistry an article once. Maybe it was co-authored with Aragoni, I'm not sure.
Yes.
Yeah, with co-authored with it. Yeah, about deuterium, hydrogen. It's interesting to read the history of it, because at first, after deuterium was discovered by Urey in Chicago in the 30s, people didn't believe, that you could actually see a chiral optical effect. And so it's an interesting thing to look at. Now, I mean, this is nothing special here. Everybody knows you do. But of course, you get very small optical activities. And I still remember Chris Andriola, who was the graduate student at the time, called me up at home. He'd been working very late in the lab, And he said, Professor Green, you know, he made the polymer that day, and it was late, and I went home. And he called me up at home, and he said, it has a very large optical activity, but something is terribly wrong. I said, what is it? He said, well, it changes constantly. The optical activity, the polarimeter was moving wild, crazy. Well, it was a day. See, we didn't have air. In Brooklyn, the labs were very old, and we had no air conditioning. And it was some kind of weather system where the lab temperature was changing. And it wasn't changing that much, but it turned out that that number is very temperature sensitive. This is at 25 degrees, let's say. So that was interesting. And he also made this one where we put the deuterium center closer. Also very small optical activity and very large. When you had it here, once removed, positive, a little closer, negative, but so what? The fact is that these were rather large numbers. And you take the circular dichroism, so the number, what does the number tell you? Well, the circular dichroism spectrum, this is the ultraviolet spectrum of the chromophore, which is the helix. The helix is the chromophore. This helix was of great interest to Bob Woody because it's like a protein that's missing the tetracoordinate carbon. It's as if you take it, like in a protein, you have this kind of thing with a hydrogen off here, but you're separated by a so this is like a protein with where you plucked out the tetracoordinate carbon, and that was interesting quantum mechanically to people interested in chromophore as a biological system. So Woody was interested in this.
What was the molecular weight of this?
Well, I'm about to get to that. The one that he made first was very high molecular weight. That's why it had such a strong temperature dependence. I'll show you in a moment. I'm about to show. So at any rate, so this large chiral optical effect was coming from the helix. It had nothing to do with the deuterium. The deuterium was doing something to the helix. Well, that's what we thought. You know, that maybe this small thing would have a large effect. So that was okay.
The cyanide is just the user.
I'm sorry?
Polymerization. Did you try to take something else? So not taking chiral isocyanide, but let's say non-chiral one.
What do you mean?
Cyanide by a nucleophile that carries the
You mean without the deuterium?
Yeah.
Yeah, sure. If you do it without the deuterium, you get 0, 0.
Yeah, but if you take the sodium cyanide, which
yeah.
is the anionic catalyst,
Sure.
something that carries a chiral information, let's say, but which could detect an isocyanide and then should propagate.
I know. You get 0. But you don't get 0 in all polymers. You get 0 in this one for a reason that I'll tell you about in a moment.
Yeah.
But you don't get 0 in all polymers. In fact, a very dear friend of mine in Japan, Yoshio Okamoto, did this experiment, but not with this polymer, but with a different polymer, a polymer that had an all-carbon backbone, and every third carbon there was an ester, and on the ester there was a carbon with 3 benzene rings on it. It's called trittle.
I see. Yeah.
And in that case, the experiment that you desire was quite successful and led, in fact, to the beginning of a career that has taken him quite far in making materials that you pack into columns to separate enantiomers. That work eventually led to Dicell Corporation packing the columns based on Yoshio's work with derivatives of cellulose. And these are the best columns now available for separating mirror image isomers of all varieties. So your experiment is an interesting one. And the reason it doesn't work here is associated with what I'll show you. You see, in the first PowerPoint that I put up, there was a word here saying dynamically racemic. See, in the absence of any information like this, these polymers are dynamically racemic. Well, we didn't know that they were dynamically racemic, but we imagined that they would be.
Isn't this right?
I'm sorry?
Better to say meso compound, meso polymers,
No.
because racemic must be a mixture of the two chains.
I know, but
But
they're internally racemic. And I'll tell you why I don't like meso. See, Larry is going to go, all right.
They're simply achiral.
No, they're not achiral, they're chiral.
No, it's
No.
achiral because there's no optical activity there because you've got dynamically switching between internal.
I know, but if you
it's
take
like
out-
a double well thing for a single
I know,
molecule.
Larry, but
switching
if you take out a single chain,
yeah.
you may find within one single chain that the left and right helical parts may not be equally populated in one single chain. And this, in fact, is the case when the molecular weight is small. See, when the molecular weight is small, you have here a true chiral racemic, a true racemic mixture, which of course is chiral by definition. So you have to, it's a tricky business. We're going to talk about this later, about this thing. You know. Okay, Larry?
Mhm.
Now, what was I talking? Oh yeah. So we imagine these things were dynamically changing from left to right, and that's why, even if you induced the system by your experiment, you know, through some initiator, which could be a spectator, which was the case in Yoshio's work, it was a spectator, followed along the chain. See, as it grew. Yes, it would say, okay, be left, you know, fine. But after it left, you know, then it would go back to its old ways because it has this capacity.
But
See,
it doesn't stay covalently attached to one end of the
that's
polymer.
right. Well, no, now if you keep something covalently attached at the
Yeah.
end, this has been done.
Yeah, I thought that this is the role of the cyanide, so it attacks the
Yeah, it stays.
isocyanide,
Yeah.
and then it propagates by the amino of the isocyanide. So, but the cyanide,
Cyanide stays attached.
Stays
That's right. If you keep something attached at the end,
Yeah.
then you will get something out of it, but not a lot. And the reason you won't get a lot out of it is that it'll only have an influence in this long chain until you reach one of these arrows. When you reach the arrow, then you lose the influence at the end. So this is a case where we've, in fact, in the words of statistical physics, this is called a uniform chiral field, when you have all those deuterium atoms there. And one time, Schnee-Lifson from the Weizmann Institute was visiting New York with his wife, Hannah, giving a lecture at the Courant Institute of Mathematics in New York University. And my colleague and dear friend, Herbert Marvis, now still doing well at 92, said, you know, Mark, I'd like you to meet somebody, Schnee-Lifson. I hadn't heard of him, didn't know who he was. And we met in a little luncheonette in New York, and I told Schneier about this experiment, and what I thought was going on. So Schneier said, you know, in my drawer, in my office in the Weizmann Institute, many years ago, I created something called a partition function for a system, not necessarily about chirality, where there was a combination of a very tiny energy and a much larger energy. And between the tiny energy and the large energy, the system was controlled. And he said, I would love to apply that to this thing, because when I spoke to him about it, that's exactly what I said. I said, you know, strung along here are all these things which have to be very tiny, and the cooperativity of the amplification has to be associated with the restriction that many, many units have to do the same thing, until they escape where this arrow comes, the helical reversal. And we did that experiment. At first we did it crudely, and it looked like it fit. And then later, because of my friendship with Yoshio Okamoto, and I went to Japan on sabbatical and spent 6 months over there, and I met Akio Teramoto, who was a wonderful polymer physicist and a student of Takahiro Sato, and they had marvelous machinery separating. We knew how to. They had worked on these polymers because of the physics problem, the original physics problem that I described, and so they knew how to take it apart. So we were able, in collaboration with my Japanese friends, to get a whole bunch of molecular weights precisely defined and quite narrow. I mean, not they weren't perfect, but they were very narrow molecular weights. So we could study all these as a function of temperature and as a function of length.
What about if you are using mixtures of butylated and protonated? Now, if you take a certain polymer of a certain length, with the composition of the interior system, there is not 100%, but
It would be diluted.
Yeah, and how did dilution affect the...
Well, that's the experiment I'm about to show you next, but not with that material. I'll show you that next. That's the experiment. Anyhow, the shape of these curves makes perfect qualitative sense. Because when you have very short chains and you're down here, the chains are not long enough to accumulate the energy to make a reversal. So any information you put must be magnified, amplified by the length of the chain. The length of the chain is the amplification. When you're in this region down here, which is down here. So the longer you make the chain, the bigger the optical activity, because the larger the energy favoring one helical sense over the other. And that's what happens down here. See, down here, it doesn't, in temperature, it doesn't matter. The only effect temperature has here is a minor effect that temperature normally has on an equilibrium, which is a small effect of this variation in this case. So here we're accumulating energy favoring one helical sense over the other as a function of the length of the chain. But eventually, these chains grow into these chains, slowly. And that's happening in this region right here, makes sense. When you start getting long enough to incorporate that the energy is enough to incorporate a helical reversal, then the length of the chain doesn't matter anymore. The only thing that matters is the number of units between these reversals. That's what defines the cooperativity. And so here, I'm sorry.
Can you explain maybe the vertical axis then?
This axis?
Yeah.
This is a chiral optical effect.
Yeah. Oh,
Circular dichroism
for the entire
optical
sample.
activity.
Yeah.
Any chiral, it doesn't matter. It can be any chiral optical effect. I'm sorry, excuse me.
Yeah.
And so when you get out here in these very long chains, then the length of the chain doesn't matter, which is why these curves are essentially flat. A little bit, but essentially not. But the temperature has a huge effect. Why? Because these are dynamic states, and they're activated states, and their population is determined by their energy according to the Boltzmann distribution. E to the energy over kT. So when you lower the temperature, you'll get fewer of them. If you get fewer of them, then the number of units between them is more, and you get a higher optical activity. And when you raise the temperature, you get more of them.
I mean, each chain has has the opposite qualities. Each chain, right? For the long chains.
Yeah. Oh, yeah. When you get a reversal, the reason you have a reversal is that you're changing. This is left and this is right.
Yes.
Sure.
And so shouldn't you have zero then?
I'm sorry?
And why don't you have zero?
You mean no optical activity? I'm sorry?
There's chiral information.
You do.
No bias.
Because we put in, see, look, see this,
Yeah.
that chiral center
Yes.
is informing this system to favor one helical sense over the other.
So it's all finishing up with the same helical sense all the way along.
Well, if you made
low
the
temperature.
if you made the temperature low enough, yeah,
Yes.
so you get rid of all of it, and we've done all of that.
Could be there a secondary Proteus effect? I mean, if you think about, let's say, that these helical chains are now enforced to interact, then there may be a difference whether a plus helix interacts with a minus
You
helix.
mean in a system, you mean the cooperativity between.
Yeah, right. If you impose, let's say, some kind of organizational constraint.
Absolutely, yes. That's a very, very interesting question because, see, there was a German student named Baumgarten who proposed in these systems that you could get, what's the magnetic effect that you get at low temperature where everything...
Curie temperature.
Yeah, but there's another name for it, where you go all the way over, where all the spins go in one direction. Is that the Curie temperature?
Yeah, this is the...
That's called, but it's called...
Ferromagnetic.
Thank you, yeah.
Ferromagnetic second order phase transition.
You could get a chiral ferromagnetic effect here, Baumgarten. And when he published this paper, I showed the paper to Schneier. And I said, Schneier, what is, Schneier said, oh, Mark, I was the referee on that paper. It's okay. So I said, really, that's interesting. And so I went in the lab with my students. We were already working on liquid crystals because, see, the system, what you're describing is a liquid crystal. That's the only way you could get them close enough. And these form liquid crystals because they're stiff. And they form lyotrophic liquid crystals, which are, of course, commercially useless. Nobody wants such a thing because you can't do anything with them. When you with Kevlar, you can make wars, and Kevlar is good for that.
So don't they take, for example, the X-80s?
What?
X-80s, which are forming the X's. And if you look at the crystal structures, many of the X-80s, they undergo spontaneous resolution.
They are what?
They undergo spontaneous resolution, which means the contact between the LL and DD X's are even better than the DL.
That's right, but and that's exactly what we in the JSCS. I can show you the reference if you're interested. You wouldn't want to see the trouble we went through to find out that these are like the hexahelices. They like to be with their own kind more than the other kind in the liquid crystal, which means that Baumgarten's idea of a ferrochiral effect, that's the word I was looking for, could in fact happen here. And we looked for it a little bit, but I've gotten too old to try as hard as I should.
But why would he suggest there's an analog with the ferromagnetic phase transition? See, that's a higher order transition. And it's because the order parameter has this, you see, the ferro would be associated with a higher order transition rather than a first order.
Well,
That's because the chiral order parameter is a time-even pseudo-scalar.
All right.
Well, no, it's in the Landau theory of phase
No, but then
transition.
you're going to get over.
Well, it's very, very simple. Yeah. I'm just wondering, did that come into his argument? Because I was going to mention this in my talk at the end of the symposium.
I'll give you the reference. We'll look at the reference together. That's what we're supposed to be doing here. The Axel's paying us to talk to each other.
Right.
But I'll tell you, yes, I'm
I
sorry.
was just curious, did they actually observe chiral domains in that situation? Because in a ferromagnetic phase transition, you get domains.
Yes. Well, we didn't observe it, but it's predicted.
Yeah.
We haven't observed it. You see, Larry, the way this ferrochiral effect is understood by me in a qualitative way is that the helical reversal is an energetic state. As you rob the system of energy by lowering the temperature, you exclude these reversals. If you're in a crowded situation, then in fact, and the reversals are excluded, then every chain will have to be all left or all right. If left-handed chains like to be near left-handed chains, and right-handed chains like to be near right-handed chains, then the system will separate into this young woman's domains. If we put a little a piece of information in there, a little some chiral thing, you know, then the whole thing can go over. What's that?
Chiral magnetization.
Something like that.
Well, it's
Then
like
the whole
it's-
thing will go over in one direction.
It's analogous to the ferromagnetic phase transition in the presence of a small external magnetic field.
Yes.
Then that makes it all point in one direction.
Exactly.
And changes the critical exponents. They change from a third to a half to a third or so on.
I'd love to show you. We'll look up Baumgarten's
Yeah.
paper. Okay. Baumgarten, by the way, left science, I heard, and has become a musician. Okay. So these lines passing through these points, that's Schneider's partition function. Beautiful stuff. And not only that, you know, when you fit these kinds of things, you can often end up with a mess. You know, like you change this, and if this goes like that and that goes like that, then it'll fit here. If this goes, this was not one of those ways. It was a beautiful. It fell into a beautiful well. You know, this way. And the number that came out of it was without question. But these guys cost 4,000 calories, not kilocalories, 4,000 calories. You want one of those, it'll cost you 4,000 calories. And the deuterium effect is very close to 1 calorie. In other words, about 1/600th of ambient energy. An energy that's so tiny that you would never see anything if it were not amplified. On a normal equilibrium, you know, forget about it. So that was very nice. And of course, the 4,000, I got a great pleasure out of that because then I could tell the physicists, forget about it. The reversal is not causing the limit to the persistence limit, gentlemen, ladies and gentlemen, because there are too few of them. You know, 4,000 is, you know, you only see 1 in 1,000 or something, or 1 in 800, and it's just not. And then a friend of mine did one of these calculations where you put in little random motions, and that was the whole thing. So we could solve the problem coming at it backwards through stereochemistry that physics couldn't solve. You know, they couldn't distinguish. Not that anyone would care. It doesn't matter. We're not going to be able to make better bonds. So what's the use? Now, so that was a lovely thing, and
There's something, in crystallization, for example, when you also have this kind of cooperative effect. If you take a monodeutylated system and you take a non-deuterated system, you don't see that such effect.
well,
Now, if you take, let's say, L-lysine deuterated,
Yeah.
big, and you like to look at the two crystal structures,
yes.
it is a question of cooperativity, can you say?
Well, you
Yeah.
don't. The problem with it, you see, cooperativity is very important in crystals. But you have in crystals something else. You have very large forces at work. See, here the cooperativity is standing all by itself. There's nothing else imposed on it, which is not true in crystal. Now, later, if you like, I'll show you an example of the mixing of polymers, where deuterium makes a huge difference. Because in that mixing of polymers, there's no crystal force. It's just a mess. And the little, in other words, what has to be true here is not only cooperativity, but the cooperativity is in control.
So if I understand it correctly, if we take molecules like alkenes,
Alkanes.
in other words, not having
I mean,
groups
like
that can form,
decanes.
yeah, or something that you don't have, that's a group that can give, let's say, electrostatic interactions or hydrogen bonding interactions in the system. Then you have a chance to see, let's say, if you take a mixed crystal, the stability is not completely
Well,
relevant.
instead of decane, would you take polyethylene?
Yeah.
Polyethylene shows that. If you try to mix deuterated polyethylene and not deuterated polyethylene.
Polystyrene doesn't also.
That's right. I'm going to show you, in fact, I wasn't going to talk about that today, but we have an example of polystyrene mixing with another polymer where the deuterium makes a huge difference.
But in our monomers, when we using purely decorated alpha 1L and deuterated, and we try to test actually the random distribution, they are completely random. So now what you might be above a certain molecular weight in order to be able to actually
You have to, that's right. The cooperativity has to be controlled, which requires the molecular. Okay. What time are you talking, Larry?
1:15.
After lunch, yes.
2 hours. Okay. Now, so what is it? Oh yeah. Where was I? Now there was a point I wanted to make about that previous thing. You know, when Schneider, when Schneider and I went to work with Lipson, you have had experience. What a treasure! I mean, this guy is really. In fact, I don't know if you know that Lipson told me this. Karplus from Harvard gets a lot of credit for molecular mechanics and stuff. But Mislow told me, and Schneider would never say that. Schneider's mathematical insights and techniques that brought to chemistry the field of empirical force field calculations, sometimes called molecular mechanics. And his students started Biosim in California using Schneider's computer model, all this type of stuff that you use for molecular mechanics calculations. He was an absolute treasure. So when we got the 1 calorie out, Schneider and I said, well, what's it from? What's the 1 calorie from? Maybe it's a special kind of a hydrogen bond, CH to N or something. And I looked through the literature, and in the end, let's take the infrared. Of course, where it fundamentally comes from is not a structural argument at all. Because where it fundamentally comes from is the 0 point energy. See, what you're learning in that deuterium experiment on the previous PowerPoint is that when you put the deuterium in a certain position and the helix is in a certain sense preferred by the deuterium in that position, that the 0 point energy of the CD bond, that if you have 2 hydrogens there, that hydrogen that the deuterium is replacing has the lowest 0 point energy. So then you get the benefit of the deuterium there. That's what lowers the energy. It's a 0 point energy difference. It's called a structural isotope effect. But that doesn't tell you what the source of it is, because then you say, well, why does the pro-R hydrogen, when the helix is left-handed, let's say, I don't remember which it is, you know what that means by pro-R, pro-S? You don't know what that is.
Pro.
Huh? Should I teach you?
According to Prelog, you never use this pro.
That's okay. Should I prelog this? Never mind. It doesn't matter. Look, let me just tell you this quickly. You don't know about this. Look, excuse me. Let's say you have a hydrogen. Let's say you have a hydrogen here and a hydrogen here. Yeah? And here you have 2 different groups. The relationship between these hydrogens is the same as the relationship between 2 mirror image molecules. And Mislow uses a word for this, enantiotopic. See? And what we've done is replace each of these in turn with deuterium. So we know something about the 0 point energy of these when this is left or right-handed. The 0 point energy changes. One is lower than the other according to the handedness of the helix. So we know all about that from the result. But we don't know why one of these should have a lower 0 point energy than the other, just because the helix is left or right-handed. This is a question of physical organic chemistry. That's a question that is addressed by chemists interested in structure, interested in hydrogen bonds, interested in dipolar interactions, interested in steric effects, interested in all the things that drive chemists to feel that they know the reasons that molecules behave the way they behave. But what we came to realize from this experiment with the deuterium was that we were in a realm of complete ignorance with regard to applying any kind of insight of that type. And the reason is that when you look into it, that insight is only useful when the effects are worth more than several hundred calories. Below 700 calories, structural theory in chemistry is completely blind. You cannot do anything when you're below several hundred calories. And here we are, 1 calorie. Forget about it. You can't do anything. So this is teaching us a lesson. If you deal with cooperative systems, not like crystallization, which are controlled by large forces, but cooperative systems that are controlled only by that cooperativity that amplifies so that small effects are involved. And to some extent, I think protein folding has important components like that. And I've spoken to people interested in the protein folding problem about this question. For example, in protein folding, it's well known now that hydrogen bonds of hydrogen attached to carbon are involved in cooperative ways. And these are almost invisible, not quite. They're not still small enough.
This is why you need homochirality, because a heterochiral polypeptide, there's no chiral bias. If it's all homochiral, then you have a bias to one-handedness of subsequent helices and whatnot.
I know, Larry, but the homochirality of proteins is overwhelmingly, it's determined in an overwhelming way.
You cannot get completely ignore weak CHO interactions?
No, I don't think so. I don't think you can completely ignore it. A friend of mine at NYU, Neville Cullenbach, I have references to that I can show you, to the effect of CHO in proteins.
But only if there are a lot.
Well, there are a lot of them.
Well, crystals, they are clear.
Yeah,
crystals, they are clear.
There's a book written by a fellow from India and England. What's the name of those?
It's a Raju, but I think that
the Raju.
It's a Raju, but this was discovered actually first, was raised by my colleague Lenderowitz, and then by Olga Keller.
I know Olga Keller's paper in Jackson. I know that whole literature, I think. And it's a very interesting literature. Go back on and see that kind of thing. Because we discovered it in a polymer blend, which I'll talk to you about soon.
So what was the meaning of this pro again? You emphasized pro.
Well, they're just given... Professor Lahab doesn't like the word, so
I heard this from friends.
I'm frightened to use it. No. What Prelog doesn't like is the word prochiral.
Pro in general.
He doesn't like prochiral, and I despise that word. But to use this, the point is that these are related as if they were the same as mirror image. What does that mean? It means that if you have something chiral, like an enzyme, the enzyme can tell the difference between these. If you have something that's not chiral, like some general catalytic agent of some kind, then you can't tell the difference between these.
But only if there's...
Mark.
What?
You just replace this group by another group, and then you get the chiral system.
Well, I know, but I want to explain it. I mean, Axel doesn't care about that so much. Axel cares about, look, I want to show you
So the other group is already chiral.
Yeah,
Right?
no, these are not chiral. May I show you something else? Do you know what this molecule is? Do you know what that molecule is? It's called glycerol.
All right, yes.
It's called glycerol. It's
Yeah.
in your body.
Yes.
It's triglycerides,
Mhm.
that we have too much of, killing us. So it's made from this. There is a point in nature. This is a fatty acid attached, where these two are free. And another fatty acid will come in here, and another one will come in here. There's a point where that happens biologically. Even though you end up, in the end, with the fatty acid here, you can't tell the difference, because in the end, still the enzyme chooses one of these to go first, and the other one to go second. There's nothing chiral about this, but these OH groups are related to each other as if they were mirror image isomers. And just as an enzyme can distinguish between D and L amino acids by the identical principle, it's the identical phenomenon, the enzyme can distinguish between these hydroxyl.
I mean,
for the same reason.
Wasn't this the molecule where you can actually do a transformation to a chiral molecule?
Well, it will. As soon as this is what Maya is saying. As soon as you put one fatty acid on here,
Yeah, but even without it.
you make it. No, without it, it's not chiral.
Not in this form, no. But I thought you could have a form which is chiral.
No.
I mean, what was this anal thing? I need to
No,
look
that's
up.
different.
It's different, yeah.
That has to do with something else.
Yeah.
But this is as soon as the enzyme approaches, then that entity is chiral.
Yeah.
And so when the enzyme approaches here, when the enzyme approaches here,
Sure.
you have what are called diastereomers.
Yes.
Because when the enzyme approaches here, the enzyme is a fixed chirality.
Okay. So what's then the difference between achiral and prochiral?
Achiral is non-chiral.
Yeah.
Prochiral is that if you have a certain group and you place one of the groups with another group, it becomes chiral. I can give you a simple.
Prochiral is still achiral.
Yeah.
It's a special sort of achirality.
Yeah.
But the transformation, a chemical transformation, converts the prochiral compound into a chiral.
Yeah, sure.
So the transformation here would be to replace H by D,
Yeah,
or let's say
sure.
and then you see that you end up with enantiomers. Another source of prochirality are usually, for example, planar groups like carbonyl groups. If you add something to a carbonyl group, there's a difference if you react formaldehyde with two and acetaldehyde. So acetaldehyde is a prochiral compound, or it's formaldehyde. So these are the two sources of prochiral.
You want to hear a good story? Larry can talk tomorrow. There's an interesting story about this. I don't know how many, but you should know about this. Citric acid has these kinds of groups.
The Krebs cycle.
The Krebs cycle, tricarboxylic acid cycle. It was observed many, many years ago in citric acid. Two groupings in citric acid which were structurally identical, just like these two hydroxyl groups or these two hydrogens. And yet, you could tell from labeling experiments in the citric acid cycle, in the Krebs cycle, that only one, when you went around the cycle, only the one that was taken and the other one was not touched. And people said, what the devil is going on? And biochemists tried to, this was before this concept of an antitopic and all, they worked it out by thinking of things anchored, and you could see that there was a difference. But you know what was fascinating about that? That I always loved this. Citric acid is made from an existing molecule called oxaloacetic acid, and then a 2-carbon piece is added that came from the digestion of fats or sugars. When that 2-carbon piece adds to the existing molecule, then you go around the cycle and chew up some of the carbons and leave some behind. You always chew up the ones that were there first. You only chew up the ones that were there first. The 2 new ones that came in are allowed to live for a whole cycle. The ones that were there are converted to carbon dioxide. It's exactly an analogy to life. The young, the new replaces the old.
Amazing, yes.
It's a fascinating business. You see it in a microscopic way. Many ways you see this. You know, I love that. That has to do with this concept in antiotopic. The enzyme can distinguish between the new coming in and the old that were there, even though once the new comes in, they're structurally identical because of this business.
You can do it much easier with your two ends, right? You have to connect there and antitopic.
Perfect.
The two ends are an antitopic. But if I'd like to shake hands with you, whether left-handed or right-handed, you find
Okay.
the equivalent.
Now, I want to tell you something else about the other lesson that we learned here. I'll stop after an hour, and then maybe I can. You wanted me to give another one tomorrow, anyhow.
Sure.
No, but I can finish. We took that polymer without the deuterium, forget about it, no deuterium, no, just the one that's zero optical activity, and put it in solvents that were chiral solvents, where the solvent had a chromophore away from the chromophore of the helix. And sure enough, you know, this is another uniform chiral field because the solvent is optically active, is chiral and not receiving. And it's influencing the helix to go in one direction, just like the deuterium was. Now, it's interesting. When you look at the effect of these solvents, R2-chloropentane, R2-chlorobutane, R2-chlorohexane, R2-chlorooctane, R2-chloroheptane, they're all the same, just the length of the chain, and yet some of them ask it to go one way and some ask it to go the other way, and so you say, oh, that's very interesting. It's kind of salvation effects. Why are these doing this? Well, you know, when we applied Lifson's partition function to this system, you know what we found these energies were favoring one helical sense over the other? They're very small optical activities, you know, the simple dichroism. You don't get a large excess, but you get some. The energy of the chiral salvation is in the ballpark of 0.04 calories per mole. 0.04. Yeah, per mole. For 6 times 10 to the 23rd units. 0.4. It's almost invisible. Now, here again is a failure of structural theory. You cannot, it's completely uninterpretable. You cannot say anything. We used this, by the way, and we published a paper later in the JACS, where we use this effect to look at a phenomenon called preferential salvation. Playing tricks with this phenomenon, but you will never know in any predictable future that I can imagine in chemistry why, how this thing fits in and does. The structural theory is it's completely lost.
Why is it that, okay, you say it's a very small optical activity,
Yeah,
so
sure, because the effect is
there's only
very
a
tiny.
small excess of one particle over the other.
Yeah.
But why doesn't that then small excess of one sense of helices over the other act as a sergeant and force the whole thing to snap in the same direction?
Well, it's not the cooperativity. Even with the cooperativity, it doesn't add up enough to overwhelm the reversal.
So the presence of just a small percentage of homochiral monomers, but all the rest are achiral, that has a much bigger effect than than what's going on here.
Yeah, well, it depends on the energy of the per unit interaction. So anyhow, so these are the lessons that we learned from this kind of system. So at that point, I said, well, cooperativity. So what's cooperativity? Well, the military works on cooperativity, and also democracy works on cooperativity. I mean, this. So the next thing we did was a military experiment. How do I do this? This is not the original experiment that we did, but it shows the case very nicely. And so here we took the chain, which was all helical. Yeah, you took the chain that was all helical, and you didn't put a uniform chiral field on it, in the words of statistical physics. It wasn't a uniform field. Instead, you put a quenched random field. That's how statistical physics people talk. quenched random field. In other words, you randomly just threw some chiral information along the chain here and there. And the proportion that you throw along the chain is right here. This is the fraction. And the chiral information is here. This comes from citrus fruits. Citronella. You can make this thing from citronellic acid. This is citrus fruit. And this is, an achiral group. So most of the chain it has no information to be left or right-handed. And every once in a while we throw in one of these pieces that we got from a citrus fruit. And you can see it's enormous. Look, very, very little stuff. Very, very small movement along this axis gives huge optical activities. And when you just have a very tiny amount, you're way up, you're right up there at the top. Sergeant and soldier. Left, front, right. But, have you been in the Army? I was in the Army.
Mark, that's the sergeant miss the carbon.
What?
The sergeant seems to me to miss the carbon.
No.
Because if this is citron...
I know it should be 10, but we got rid of one of the groups.
Okay.
We did a reaction where we got rid of the carboxylic acid at the end of it. But the good, that's, the terpene rule. So that's the great Yugoslav, the great Yugoslav chemist who ended up at the end.
Okay. Everything in life is either concave or convex. If you think more...
When the curve goes flat like that, are you assuming, do you know that you've got...
By the way, this is just some dirt got on here. That's not the point.
I mean, is that 100% homochiral
Yes, it is.
helix?
Yeah.
You know that?
You know how we know that? We made the whole polymer of this stuff.
Oh, okay.
And you get the
It's
same optical activity. So this was, so I said to Schneider, write me a partition function. He said, Mark, I'm already over 80 years old. I said, so what? Look at you, you're active. He said, I can't. I have to write a different partition function for every chain, unless, he said, you tell me where these sergeants are in the whole ensemble. And then I'll write one partition function. If you can't tell me that, I have to write a partition function for every chain. I said, oh my God, really? Such a precise business, this partition function business. So at that point, a young man named Jonathan Selinger, who contacted me through a friend, was interested in statistical physics. And he said, I'd love to do that because I would like to apply theories of paramagnetism, one-dimensional paramagnetic states, Ising models of one-dimensional paramagnetic states. So he wrote an Ising model for this. H Hamiltonian equals a summation, of which contains in it the energy of the reversal state, and then the second term is a summation of how much this desires left versus right, and in that case you had to put the energy inside the summation because it was a quenched random field. In Schneider's Ising model, Schneider never used an Ising model, but it was the equivalent. You could put it outside because there was a uniform chiral field. And this is all statistical physics type stuff. And then Jonathan, so what are you going to do with an Ising model? Forget about it. But then Jonathan made within some limits, specifically of this term here, he could make an algebraic expression out of that Ising model, and this is the algebraic expression. And so this is the chiral order parameter. I think someone was using this word before. So what's this? This is simply the optical activity observed, the chiral optical effect observed, divided by the full chiral optical effect. So it's an order parameter. And here's R, which is this axis here. How many sergeants do you have in there? L is the number of units between the reversals, which of course depends on an energy of the reversal, which we discovered was 4,000 calories in that other system, but it's not that here, it's a different number. And because the solid soldiers here are not hexyl groups, they're branched groups, so and that makes a difference to how difficult the reversal is. And RT is the usual meaning. And this hyperbolic tangent is what you call a saturating function. It's related to, you could think of it, if you draw a Gaussian curve, and then you have a line down the middle that's 0. If you move off that line a little bit, you get a lot. Because the curve is like that, you get a lot. But if you are here, you move the same distance, you get almost nothing. So it's a saturating function. And that's what this is. And the shape of the Gaussian depends on the details of the energies. So that was very nice. So Jonathan, that was a quite successful, nice experiment with the sergeants and soldiers. So if we could do, and by the way, these phenomena that I'm describing, you see, the reason we stuck with this nylon 1 for so long was that it soon became apparent that this was a model system. And in fact, the literature now is full of all kinds of things, from supramolecular helices to all kinds of covalently bound helices. It's a big literature. Every time someone studies a helical system which is dynamic, in other words, in which left and right are possible to change into each other, these rules and partition functions and Ising models, they all apply. So this turned out to be, just by luck, a model for a wide variety of helical systems. You're finding out here about helices in general. So now it's time to get out of the military into I'm talking already over an hour. What do you want me to do? Continue?
I mean, as long as we can get to lunch by sometime after 12.
All right. Well,
I mean, the queue becomes longer by 12.
Well, you shut me up when you like. It's Maya's and Larry's fault they ended. So what's democracy majority rules? So we figured, this would be fun. Let's take the polymer and sprinkle along the polymer units that want it to be left and units that want, and enantiomers. This unit, you'll be right-handed helix, and the other one wants left-handed, and you mix them close to make them neighbors, random with each other, and let's see what'll happen. I mean, you can imagine what'll happen. The helical reversal is difficult. If the units that want to be left and right, if one is in the minority, if it's willing to put up to be in the wrong helical sense, it may be okay, because it may be easier for the pain of the minority to be in the wrong helical sense than to impose a helical reversal every time a couple of minority groups come together. That's the source of the majority rule, and it's really the source of majority rule in all democratic systems. That the minority who lose the election are willing to put up with living in the regime of the majority because they don't want to have a phase separation, split the country into different parts. It's the same thing. It's absolutely identical. So Jonathan Selinger wrote an Ising model for this, which is similar to the other Ising model. And again, an algebraic, you can get an algebraic expression by making some limits, For example, here's that order parameter, the optical activity compared to the full optical activity. Now you get not a hyperbolic tangent, but an error function. But an error function is also a saturating function that can be described in a similar kind of a way. But now you get some different parameters in here. Here's L. That's the distance between the reversals. That has to be there. The larger L, the bigger the effect. R is the chiral fraction, and we're going to come to that in a second, because you see, you can imagine a polymer in which every unit wants the helix to be left or right. In other words, every unit is chiral, but of a different direction. But you could also imagine a polymer, like the sergeant and soldier polymer, where many of the units don't care, and a few of them, instead of being sergeants that want everything to be left-handed, some of them are sergeants that want everything to be right-handed. In other words, a combination of the two experiments. You see? So R says that we can play the conflict game where the sergeants are conflicting. Come to that. You see what I'm saying? Yeah?
Mm-hmm.
This is the chiral, P is the ratio is related to how many left units and how many right units do you have, you have, how big is the majority, that's P. And 1/2 is simply the fact that we're dealing with enantiomers here. So the free energy of one enantiomer favoring the left-handed helix and the free energy of favoring the right-handed helix are equal and opposite, and that's where you get the 1/2 from. So this term tells you that if you put in 50-50, I want left and I want right, this is going to be 0, and that will be 0. Nothing special. What's really special is L. Now L can be determined if L is the length, if you're in a short chain regime, so L is determined by the chain length, by the number of units in the chain. That's uninteresting. On the other hand, L could be determined by the population of reversals thermally. They're worth a certain amount of energy, and you have a certain temperature. That's not interesting either. What's really interesting is what's called L with a random field. In other words, if you're in a regime where the chain is long enough where the length doesn't matter, and where the temperature and the energy of the reversal are such that the thermal reversals don't matter, then L is limited by what's called a random field. A ratio of free energies. The helical reversal energy is on the top. Makes sense. The higher the energy of the helical reversal, the larger any value of L will tend to be. So it makes sense that if the helical reversal is difficult, L should be bigger, no matter how L is defined. But what's really fascinating about this is the denominator. You know what this is? This is what I was talking about before, the chiral bias energy. In other words, this is the energy by which the sergeant wants the helix to be left-handed or right-handed. But where the competing enantiomers favor one helical sense over the other. That's the free energy that they favor things by. Delta GH, by the way, for the deuterium was a single calorie. So you can't use this approximate algebraic solution of the Ising model has limits in delta GH. If your delta GH gets too small, then you can't make this algebraic system. You can't solve the Ising model with this system. But within certain reasonable limits of delta G sub H, this algebra applies. This is really a fascinating thing because what does that mean? It means that as delta GH gets bigger, as the force of the chiral entity is more powerful, asking for its helical sense, the cooperativity goes down. Which means that a larger chiral force will cause a smaller optical activity. That's what I'm saying. And when you think about that, you say, that's ridiculous. But when you think about it for a moment, you realize that although it's counterintuitive, it actually makes perfect sense with human experience. If you have a cooperative system, which is where people have different points of view, if you push too hard, you may in fact destroy the cooperativity. and your competitor may just go off and form their own regime, impose a helical reversal, so to speak.
But what's the lower limit? Surely the parity violating weak neutral...
No, you can't. Delta G sub H can't be too small, otherwise the algebra fails.
It can't be too small.
Right.
So would you say the parity violating energy difference...
No, those would way be...
You said it can't be too small.
No, well, I said it the wrong way, I'm sorry. I meant to say that if delta G sub H is too small, this algebra doesn't work.
Oh, sorry, okay. So that's out of the question.
Yeah, you can't.
Violation.
This is an approximate solution to an Ising model.
Yeah.
And to make that approximate solution, there are limits in what delta GH can be.
Going again to the slide.
To the what?
To the slide problem with the C13, C12. If you take here a molecule which is actually the meso,
What?
if you take the surgeon and meso,
These here?
in the previous slide, let's say you had the meso molecule. Yeah.
Here? This is not, what do you mean?
This group, if you take such group as a start and a surgeon, not
Here?
this one,
This?
this one, yeah.
Oh, this is not meso, this is...
No, but if you label one side with C13
Oh, yeah,
and one with C12,
yeah,
and you use it as a surgeon,
yeah,
and then you apply your formula,
yeah.
the question, are you going to get the same similar effect as you're getting with deuterium?
No, you won't get. And SOI's things are smaller than anything that I'm dealing with here. So SOI has in this it's a Kagan, I think, derived with business. It's a feedback mechanism. SOI's got a feedback mechanism.
Yeah, but he claims now that the departure in the first stage by putting a molecule, it creates some kind
That's
of
right. But
structural
his-
environment
but-
that goes with that.
All of that's true, but his departure in the first step is probably minuscule. His departure in the first step
Yeah,
is
but the
minuscule.
question is if you want to get some kind of a quantitative evaluation of this minuscule departure,
Yeah.
and according to your equation that you just pointed out,
You could get an
you said
energy.
that it's small. The question is, like what Larry said, how low you can go. You know,
Well,
to get an effect.
in this equation, in this Ising model, in this solution to the Ising model, there's no limit on delta G sub H. It can be zero. If it's zero, you get zero. It's
So
okay.
the next equation.
The next equation, you can't have it be so small in the majority of cases.
I'm sorry to keep banging on about the symmetry of the
Don't be
chiral
sorry.
order
That's not true. You're
parameter.
not sorry at all, Larry.
No, not at all. But it seems to me it's absolutely fundamental.
What is it? What?
It's parity odd.
Wait,
That
you want me
means-
to go back to the
No,
majority?
I don't want you to go anywhere. We've got here our chiral order parameter.
Yeah.
It's parity odd. That means it is not associated with first order phase transitions. It's analogous to the magnetization vector in ferromagnetism, which is tie-on. And in the Landau theory of phase transitions, out of that you only get higher order phase transitions. And higher order phase transitions are associated with critical phenomena. And at the critical point, you suddenly get a multitude of interaction paths opening up which spread throughout the whole system. So you get this enormous cooperativity. This is what critical phenomena are all about.
Well,
Whereas
I can imagine that happening here.
Yeah. So the point is, if you don't have chiral monomers, or if you don't have a chiral chemistry, then you lose the possibility of critical phenomena. You see, and that might be something fundamental in the physics of life, shall we say?
I'm sorry, you are still in the equilibrium.
I'm just looking for reasons why chirality is absolutely vital to the chemistry of life. And this is one possible.
I can tell you the reason without symmetry. But let's save that for lunch. I think it simply has to do with the nature of catalysis. And the fact that life is three-dimensional. if you combine the concept of catalysis with the three-dimensionality of life, you must end up with homochirality. Now, whether you end up with being on one side of the mirror or the other is a question that's not answered by that. But homochirality is absolutely essential for any catalytic system.
Looking at it from the point of view of nuts and bolts.
You can't have the best catalyst in a three-dimensional system without it being mirror image selected.
That's right. But I'm trying to stand back and look at the.
I know, Larry, but I'm just a regular kid from Brooklyn. You can't, I'm not fancy,
But it's just part of the same story. You're just saying what is the mechanism of achieving the global coherence, and you are just saying there must be global coherence. So that's the mechanism, the catalysis.
Yeah, I think
that's what you're saying.
Let's we can argue. Let's talk about that because you know. By the way, who first? I think I got that idea from Jeremy Knowles.
Oh.
And Jeremy Knowles is an Englishman, like
I
you,
used to know him.
and he became a provost at Harvard.
Yeah.
And I met him once and had a chat with him, and also, but I think it wasn't out of that chat. I think it was in an Accounts of Chemical Research article where Knowles pointed out that an enzyme has to be enantiospecific in order to be the best possible catalyst. And it makes perfect sense. You can teach that to a child, actually. How can you have a three-dimensional thing that fits perfectly without it discriminating perfectly between left and right? It's impossible. Well, anyhow, so this was this. Oh no! I've been through this already. So the prediction made is that when you lower this energy, when you raise this energy, you'll lower the optical activity within certain limits, which is a very interesting apparently counterintuitive prediction. But there's another prediction that comes out of this approximate algebraic solution of the Ising model that Jonathan Selinger came up with, and that's the fact that if you do the arithmetic, which took me a while, because I don't do arithmetic that much anymore, you find out that if you stick this in here, that R cancels out. That's really interesting, because R is the chiral fraction. So what that means, therefore, is that the chiral order parameter in a conflicting system within certain limits will be independent of the number of units fighting with each other. In other words, I could have the left and right units fighting with each other over the whole chain. Every unit of the chain has left or right fighting units with each other. Or I could have most of the chain doesn't care, and a few of them along the chain are fighting with each other. And you'll get the same result, because R cancels out. That's a nice one. By the way, this line here it comes from the. In other words, that's a fit. This is not just a line drawn by a computer. This is a fit. But this line is not a fit. This line is a line I drew from data for D and L amino acid system. But this is a fit to the data, a fit of the data to the proximate solution to the Ising. Here's the experiment. R cancels out. Now, we're not getting the full optical activity, because we're in a place in the regime here. This is 48.6% is the minority, and 51.4% is the majority. This happens to be in a place along the rise. You remember? I'm sorry. This is in this region. So you're not getting the full, you're not all the way there, but that's not what matters. What matters is that you get the same chiral optical effect, the same excess of one helical sense over the other, if you have every unit in the chain being the conflicting enantiomers, versus having most units don't care, and only a very tiny proportion are having the same conflict as here, same ratio of wanting left and wanting right. So this is the demonstration that the approximate solution to the Ising model, that R cancels out. That's a very interesting thing, because it shows you that under certain conditions you can have a polymer, and after all, what is life? But life is polymers. Everything about life, we'll get to that shortly, but everything is polymers. The search for the answer to the question that you're posing here, in my opinion, is in the property of polymers.
Are you saying, independent of the length of the helix, the same number of homochiral enantiomers will produce the same effect, independently of the length of the polymer?
Well, the length of the polymer doesn't matter because the cooperative length is determined by the random field domain, which is determined by that ratio of free energies. So this is a situation where the length of the polymer doesn't matter. The number of polymer chains would matter, because if the number of units conflicting with each other get to be too small, there won't be enough of them to be in every chain. So, eventually you'll have some chains that don't have anything in them except units that don't care. But generally, the cooperative length here is determined by the conflict, not by the length of the chain.
The position of the chiral surgeon doesn't matter. Let's say if you take the chiral enantiomers.
Take what?
You take the
Well,
chiral
we don't know where
enantiomers.
we don't know where these things are. It's a random terpolymer.
In other words, the group which stays is the initiator.
The initiator.
The first start. If you put it on the end of the chain, because sometimes this chain can reinforce the entire chain to go into something.
It's not going to do that, because this is a dynamic equilibrating system. It's like it's a complete equilibrating system. So whatever is here or there, it just throws itself into the
The question is what the mechanism of this reversal. The question is how one chain converts into the other.
Well, it could be that the reversal starts at the chain end. That's true.
Therefore,
that you see the reversal. Some physicists have described these reversals to me as like solar pumps. They can run up and down the chain and fall off the end of the chain and start from the end and move into the end of the chain. But I believe unless you put something at the end of the chain that denies entrance to the reversal, that would be essentially like denying the equilibrium on which all of this is based. Okay, so that's very nice. And we actually took the trouble, although I published it in a completely ridiculous place. All right, so we should stop. Should I stop? And I'll continue another time. Or what should I do? I have a little more to say. I don't have so many PowerPoints, but I've got a lot more to say. Actually, I haven't come to the point yet.
Yeah. I realize that would be a pity, no?
The point is not made yet. But
I do need a rest.
So let's stop.
In view.
All right.
No, I think I could use a rest too. Okay. So is there time to pick it up again
Sure.
after 11?
Certainly the optimal time is to do. We wanted to continue on Saturday anyway,
Yes, that's right.
right?
I don't think so. I'm here.
Any objections against getting together on Saturday? So then we have plenty of time. We do Saturday at 10:30. It's 10 o'clock at coffee room.
10:30, and I won't. Saturday won't be so long, and maybe also we can. Maybe there'll be things that come out of Larry's talk.
Yes, yes,
Talk
yes,
about.
yes.
What else did you have planned for Saturday?
Just free.
So, yeah, in the afternoon you said TBA.
Yeah.
All right, so tomorrow morning
Sure,
at 10 o'clock.
Yeah.
Perfect. Thank you so far. then.
Thanks a lot. Thank you.
we could, let's say, till those,
I mean, look, if you